Okay, today we're going to do the last section of a bipolar junction transistors troubleshooting. Very important part of this chapter because you are going to build various circuits and eventually also using a transistor building switching circuit and amplifier circuits. And if the circuit's not working, you have to know how to go about to find the fault. So troubleshooting. In your textbooks, you see there 4.8 troubleshooting. Introductory paragraph tells you what we're going to do in this section. As you already know, a critical skill in electronics work is the ability to identify a circuit malfunction and to isolate the failure to a single component if necessary. In this section, the basics of troubleshooting transistor bias circuits and testing individual transistors are covered. Okay, in previous chapters when we've done the diode, you did similar. Because remember, the diode also had a p-n junction. The transistor now has two p-n junctions. So we're going to treat it in a similar way, but we'll get to that when we're going to test the transistor using various methods. But let's start there at the top of the page, troubleshooting a bias transistor. You can mark as I indicated here. Several faults can occur in a simple transistor circuit, a bias circuit. Possible faults are open bias resistors, open or resistive connections, shorted connections, and opens or shorts internal to the transistor itself. Now it's important, if your circuit doesn't work, that you know how the circuit works so that at least you know what to expect, what to measure at certain points in your circuit. Anyway, in figure 438, go to figure 438, basic transistor bias circuit, as we've discussed in previous sections. Biased two separate power supplies, VBB in this case 3 volts, VCC 9 volts, and then I have to do some measurements and see if the circuit works or not. Anyway, the correct voltage measurements at the base and collector are shown. Analytically, these voltages are verified as follows. A beta DC of 200 is taken as midway between minimum and maximum values of HFE is given on the data sheet for the 2N3904 on figure 420. Remember when we just had a look at the data sheet? Mostly it gives the minimum values only, but at IC of 10 milliamps, in that specific case, it gave a minimum and a maximum. So what you have to do your calculations, analytical analysis or whatever, or fault finding, to be able to determine values more or less in the vicinity, I have to take the midpoint or the average of the minimum and maximum values. It will be for beta DC, in this case 200 for the 2N3904. A different HFE or beta DC, of course, will produce different results for a given circuit. Okay, as we can see there, on top of figure 438, you have to do some calculations, the same as that you will do in the practical class. So see, this is going to be an aid for your practicals and eventually when you have to do fault finding wherever you're going to work as a technician or an engineer. Alright, we already know VB is equal to VBE, which will be 0.7 volt for this specific circuit, and I can see that I measured that there with my multimeter on voltage. 0.7 volts, remember this is VB. VB is measured with reference to ground. So the red lead will be on the base and the black lead will be on the emitter. And I know that I will get a 0.7 volt drop approximately there between base and emitter. Of course there's no resistor on the emitter in this specific circuit. The difference between the emitter and base is 0.7 volt, and I can see that the emitter should be 0 volts. There's no resistor between the emitter and ground. Alright, then I can calculate IB, IC and VC. So I basically know what I am supposed to measure. Alright, so there are several faults that's discussed on the next page, which we'll go through now. But you have to know what you want or what are you expecting to measure when the circuit is working. So from there you can then work to do the fault finding according to the different measurements that you will get. I just have to point out again in the on the textbook here, just below figure 438, there is a term mentioned, floating point. A floating point refers to a point in a circuit that is not electrically connected to ground or a solid voltage. Solid hyphens, normally a very small and sometimes fluctuating voltage in microvolts to low millivolt range are generally measured at floating points. The figure 439 are typical, but do not represent all possible faults, of course, that may occur, but it's the typical types of faults. So let's have a look at the faults quickly, and then we will discuss how to test a transistor with a digital multimeter. Okay, if we go and look at the examples of faults and symptoms in figure 439, perhaps you'll have to follow me in your books as well, because it's not very clear on the board there. At least we can see the circuits. Anyway, figure 439A, the fault is open base resistor, and I can see what I'm measuring there. It indicates there 9 volts. 9 volts at the collector, and I've got a microvolts, seems like a floating voltage at the base. It says there the symptoms: readings from microvolts to a few millivolts at the base due to floating point, and 9 volts at the collector because the transistor is in cutoff. How do I know the transistor is in cutoff? I can see that VCC is equal to 9 volts, and I know if I measure between collector and emitter, if I see this is a switch and it's an open switch, what will I measure over the open switch? I should measure the supply between collector and emitter. So it means that the transistor is in cutoff, so the fault is most probably what is there. It could be that the resistor RB is open, it could be that the track is broken before the base, or that the base terminal is broken or not making a connection or something there. Actually, this measurement, as they show you, is just before the terminal of the base, so it should be the resistor or the track that is broken. Typically, that's where you would go look for the fault if you get readings like that. If you look at the second one, you can see the fault. They say the fault is open collector resistor. What is the symptoms? A very small voltage may be observed at the collector when a meter is connected due to the current path through the base collector junction and the meter resistance. But you can see voltage that they indicate here at the base, approximately 0.7. They show here, it's not exactly, of course now we're doing practical, 0.6 to 0.8. It may even be a bit more or a bit less. But it's not an accurate voltage, but I do have a floating point at the collector. So the same as I had in the previous one with the base resistor, could either be the collector resistor that's open or the track that's broken before the collector's terminal. Alright, then the third one there, the fault mentioned there is the base is internally open, because the symptoms is I get 3 volts at the base lead and 9 volts at the collector because the transistor is in cut off again. Alright, so I get a 3 volts meter reading there when I put my multimeter and I measure from base to ground. 3 volts. What is the supply? Also 3 volts. So I can see that the bases must be internally open, because I'm measuring up to the base and I get 3 volts. It should have been approximately 0.7, so it means again that the transistor is in cutoff. Of course, I'm measuring over this collector emitter of mine. I'm measuring a voltage which is VCC. Means the transistor is in cutoff. Alright, if we look at D1, the fault, the collector is internally open. What are the symptoms? I measure between 0.6 and 0.8 volts at the base again, as it should be. Due to the forward drop across the base emitter junction, and 9 volts at the collector because the open prevents collector current. Okay, so here again I can see there's 9 volts. There's the voltage that it should be, but the 9 volts isn't correct according to the calculations that we've made. We see that VC should have been 4.4 volts. So the transistor again acts like an open switch, but in this case, because of the measurement that I made at the base, I can see that the base is working fine. It should be the collector that is internally open. If everything is working up to the collector terminal, it must be internally that the collector is open. Fault number E, emitter internally open. Why? The symptoms, I've got 3 volts again at the base, 9 volts at the collector because there's no collector current, but there's 0 volts. The 0 volts at the emitter, of course, is normal, as you can see there, because there's no, if I measure between emitter and ground, I can see there's no resistance. There shouldn't be any potential difference, so that is normal. But the 3 volts at the base is not normal. I know that I should have measured from base to ground. In other words, the base emitter voltage should have been approximately 0.7 volts. But I do get 3 volts, and the track seems to be fine up to the base. But it means that the emitter then is internally open. Still have the 9 volts there, so it means that the transistor still is in cutoff. I still measure VCC between collector and emitter. Right, and then the last one, the fault open ground connection. The symptoms, I have again 3 volts at the base. I've got 9 volts at the collector. But I've got approximately 2.5 volts or more at the emitter due to the forward voltage drop across the base emitter junction. The measuring voltmeter provides a forward current path through its internal resistance. So here in this case, you can see there's my 9 volts, so it means the transistor is in cutoff again. 3 volts there, but here at the base I should have measured 0 volts. I am not measuring 0 volts. So it seems that there's a volt drop between the base and the emitter, but it's not connected to ground. So if I should have measured 0 at the emitter. So that is some of the faults that may occur. But the important thing is that you have to calculate the values as expected for your specific circuit. If the circuit is not working, then at least you know what you have to measure at certain points in your circuit due to current flows, etc., etc., and from that you can deduct then what the fault may be. Okay, of course, if I suspect the transistor to be faulty, I have to be able to test the transistor. To be able to test the transistor, we will use a digital multimeter. Digital multimeter we also used to test the diode PN junction. I can see here in this case that transistor, as we already know, is actually 2 PN junctions. So depending or if it is an NPN or a PNP transistor, I have to know which of these junctions will, how will I forward bias or reverse bias these junctions. Okay, so there are a few methods that I can use on the digital multimeter. I can use on the diode testing section or setting on the multimeter to do it, or I can use the ohms setting to measure the resistance. Then I should expect what to measure, as you've done with the diode as well. And the other thing is, of course, some of the multimeters has a setting for HFE where I can measure the beta. Then you should also know what the beta more or less should be, and if I get the correct beta reading or in the range because I know it's not a set value, it's a more or less value, then I also know that the transistor operates. But I have to be possible, or I have to be able to be to test the transistor in these various methods. All right, anyway, if we look at figure 440, a transistor viewed as two diodes. Let's look at the NPN first. Then the junctions operates as follows. So if I want to forward bias the NPN junction, base emitter, if I put the red lead on the base and the black lead on the emitter, then I should read approximately 0.7 volt if the junction is functioning properly. Between the base and collector, same thing. If I forward bias, red lead on the base and the black lead on the collector, I should also read approximately 0.7. It's not going to be exactly 0.7 volts. No. And for the PNP, I can see then just the polarities are the other way around. And then I should get the same reading. So if I forward bias, then for instance, the emitter base collection, I will put the red lead on the emitter and the black lead on the base, and I should read 0.7 volts. Alright, that is when it is forward biased. When I test for reverse biased, then of course for the NPN, I will put the black lead on the base, the red lead on the emitter, and what should I read on the diode testing scale? Some of them will say open line. Some of the older meters will give you the reading of the voltage of the internal battery. Okay, so it depends on how old the meter is that you work with. And the same, of course, with the base collector junction when that's reverse biased. Should act as an open, and of course again the opposite for the PNP transistor. Alright, the diode testing method is discussed starting at the bottom of the page just below figure 439. Digital multimeter diode test position, and they also indicate some of the pictures of what you should typically see on these multimeters when you are testing. So you can see there for the first one, forward bias test for a base emitter junction. Note the colors on the transistor. If you go back, let me just display these figures. Right, the colors are a bit funny on the screen. Anyway, I can see here forward bias test for a base emitter junction of an NPN transistor. Take note, you must know what type of transistor you are testing. Eh? So if I want to forward bias, I put the red lead on the base, the positive on the base and the negative on the emitter, and if it's working properly, it should display approximately 0.7. It's not going to be exactly 0.7. When I swap the terminals, you can see now that the positive is on the emitter, negative on the base, black lead on the base. In other words, I reverse bias, then some meters will display open line, some will display the internal battery, the voltage of the internal battery, because it acts like an open switch and you measure the supply voltage. That's the only reason. So if the internal battery of this multimeter is say 9 volts and it's still good, it should display a value of approximately 9 volts when it's reverse biased. So don't get confused. Some meters will show open line, some meters will show you the voltage of the internal battery. Okay, there's digital multimeter test for a properly functioning NPN transistor for base collector, forward biased and reverse biased. So I can see again forward biased approximately 0.7 volts, and for reverse bias open line or the voltage of the internal battery. Alright, that of course is when the transistor is not defective. What faults may occur with a transistor? Same as we had with the PN junction, the other device that we've discussed, the diode. The diode could either be open or shorted. Okay, normally the most common fault is being open, but of course if I test a PN junction, because I'm testing a PN junction at a time here for a transistor, if I forward bias the transistor on these methods that I've seen here, and say the transistor is open, so if I forward bias and reverse bias or reverse bias that junction, I would get the same value, which would be, if it is open line, or the value of the internal battery of my multimeter. If it was shorted, of course, if I measure a shorted junction, short means it acts like a closed switch, so it should be very low voltage, or actually close to zero, because it's like a closed switch. All right. If I go and test a transistor using on the ohm setting, okay, it's not discussed here. It's discussed in the textbooks, however, at the bottom of the page, just below figure 441. Some multimeters, of course, doesn't have a diode testing or an HFE socket, but then you can test the transistor by using the ohm setting. Now, the same rule applies as for the diode. When a transistor is good and I test base emitter junction and I forward bias the base emitter junction, it acts like a closed switch, and when the diode is good, what should the resistance be? Closed switch, so the resistance should be low, so in other words the reading should be low. I should get a low reading. If it's functioning properly and I reverse bias it, it acts like an open switch, the resistance should be high, there shouldn't be any current flowing. If the diode, of course, or the PN junction isn't functioning properly, it acts like a short, for instance, then if I forward bias or reverse bias it, it should give me a low resistance. If the PN junction is open, then of course I will have a high resistance in both directions. So remember this, if you are asked this question, of course I cannot ask you what will the resistance be. I would ask you, for these different conditions, would the resistance be low or would the resistance be high? Then you should just know, because of the characteristics of a PN junction and a switch, how it should work. Alright, what we also get is transistor testers. That's not so common, but it is available. Just below figure 442, I can see there's a transistor tester. An individual transistor can be tested either in circuit or out of circuit with a transistor tester. For example, let's say that an amplifier on a particular printed circuit or PC board has malfunctioned. A good troubleshooting practice dictates that you do not unsolder a component from a circuit board unless you are reasonably sure that it is bad, or you simply cannot isolate the problem down to a single component. The problem being, when components are removed, there is a risk of damage to the PC board contact devices. Okay, you can read that section on the transistor testers. I've got different cases there on the next pages. Case 1, if the transistor tests defective, it should be carefully removed and replaced with a known good one. An out-of-circuit check of the replacement device is usually a good idea, just to make sure that it's okay. Alright, case number 2, if the transistor tests good in circuit, but the circuit is still not working properly, examine the circuit board for a poor connection at the collector pad or a break in the connecting trace and so forth. This also applies, you're going to build your circuits on a breadboard, however. You are familiar with a breadboard. You have built some simple diode circuits, application circuits, rectifier circuits on a breadboard already. And that also happens that you may have bad connections while you are making your connections on the breadboard. So make sure that your connections are, that's the most common fault, I would say, are the connection faults. All right, the importance of point of measurement in troubleshooting. In case 2, you had taken the initial measurement on the transistor lead itself, and the open were internal to the transistor shown in figure 445. You would have measured VCC. This indicates a defective transistor even before the tester was used, assuming the base to emitter voltage is normal. This correct simple concept emphasizes the importance of point of measurement in certain troubleshooting situations. On the next page there, leakage measurement. Very small leakage currents exist in all transistors, and most cases are small enough to neglect, usually nanoamps. When a transistor is connected with the base open, IB 0, it is in cutoff. Ideally, IC should also be 0, but actually there's a small current from collector to emitter, as mentioned earlier, called ICEO, collector to emitter current with a base open. That's what the CEO stands for as a subscript. Each current is usually in the nanoampere range. A faulty transistor will often have excessive leakage current and can be checked in a transistor tester. Another leakage current in transistors is the reverse collector to base current, ICBO. This is measured with the emitter open. If it is excessive, a shorted collector base junction is likely. Transistor tester, you can also do the gain measurement, which is beta DC, of course. A known value of IB is applied and the resulting IC is measured. The reading will indicate the value of IC divided by IB ratio, which we know is the beta, and so then I can see if the beta value is as what it should be. Most testers provide for an in-circuit beta DC check so that a suspected device does not have to be removed from the circuit for testing. Also, you also do get curved traces. Is an oscilloscope type of instrument that can display transistor characteristics such as a family of collector curves. In addition to measurement and display of various transistor characteristics, diode curves can also be displayed. Some other instruments, some fancy instruments that you can also use to test transistors. But the most common tests, of course, is old reliable digital multimeter using the diode testing or the ohms setting. So please be familiar with that. What do you expect to measure? And of course, you have to be able to apply the fault finding procedures as we've just discussed. You will see if we go to the end of the chapter, we have to go and do the basic problems. Basic problems now that you have to cover for this section is 37 to 39. And then we leave out the section because you're doing your own practicals. We're not going to do the practicals of this textbook. And then again 43 to 49, which is very important. If you go and look at the basic problems there, you will see that the troubleshooting problems, as I said, starts at 37 up to 39. Then it's application activity problems. Then from 43 onwards to up to 49 are called data sheet problems. These are very important. So make sure that you understand how to use the data sheet. And here are the examples that I've told you about in the previous sections, where I have to go and look at under what temperature this device operates. So if the temperature is not at 25, it has to operate at a higher temperature, 25 degrees Celsius, then I have to keep in mind that I have to calculate the derating factor as well. So just keep that in mind. All right, this concludes then this section.